Okay, time for a real gem. There was quite a lot of rigmarole involved in proving this angle sum identity last week. We used triangles, and there was a lot to it. And I didn't write the other side of the identity here, but the idea is we want to be able to write the sign of the sum of two angles in terms of trig functions of each of those angles separately. So today I'm going to show you how you can use the complex plane and simple multiplication to derive that identity much, much more easily. And to do it, we will be taking advantage of two important properties of complex numbers that we didn't prove, but you could prove in a later course. So if this is the complex plane, where this is the real axis, and that's the imaginary axis, if we have a complex number a, which is at an angle a, maybe we should make this a different letter, lowercase a, and we have a point b, which is located at an angle of b, we could define a new complex number c that's just a times b, so the simple multiplication of two complex numbers. And if we knew what the components were, we could actually multiply them out. But instead of doing that, we're going to use a geometric property. So we might ask, if we were going to multiply this out, what's the angle that points in the direction where c would end up if we multiplied it out? And the rule is that the angle to c is just the sum of the angles to a and b. So if I take angle A and add it to angle B, about like that, that's going to point in the direction of where C is going to end up. So how far do I have to go in that direction? That's the magnitude for C, because magnitude is distance from the origin. So the magnitude to C is just the magnitude to A times the magnitude to B. And there's no scale here, so it's a little bit hard to tell how far you should actually go. But we could put C there, for example. So angles add, magnitudes multiply. All right, so let's set up the proof. If you want to follow along, go ahead and sketch out a little portion of the complex plane. That's the real part. That's the imaginary part. And we're going to be thinking about the unit circle on the complex plane. So this would be the number 1. That would be I up here. And we're going to define a point on this unit circle, which means that that magnitude is 1. And I'm going to call that A. And it's going to be at an angle of A. And I'm going to have another point here, B, and it's going to be at an angle of B. Okay, so I'm interested in discovering what is the sign of A plus B. So it would be really convenient if I had a point here whose angle was A plus B. And as we just said, you can get an angle of A plus B just by multiplying those two complex numbers, because when you multiply complex numbers, that rotates them. So I will define a new point C up here that just is A times B. And I know that the angle to C is this angle B plus that angle A. Okay, let's drop a vertical line from that complex number C, and now we have a right triangle in the complex plane. So answer this question for yourself. What in this diagram does sine A plus B describe? And I hope you said that it describes the height of that green line, because the angle for this triangle is A plus B. By SOHCAHTOA, sine would be the opposite side over the hypotenuse. I know the hypotenuse is 1 because this is the unit circle. So sine of A plus B is just that height. All right, what's another way? So we want to find out what that's equal to. So let's figure out another way of calculating what that height is. Maybe it would help if we knew what these coordinates were. Because, for example, if I knew that this point was at like 1/2 plus root 3 over 2, root 3 over 2, the imaginary component, would describe that height. So let's try and figure out what are the coordinates there. And I'm going to do that by actually multiplying out A and B. But I guess before I can do that, I actually need to know what are the coordinates of A and B individually. So if this weren't the complex plane, if this were just a normal unit circle, here, let me get a new piece of paper. So if we weren't on the complex plane and I wanted to find the coordinates of a point on the unit circle at an angle theta, it would just be cosine theta and sine theta. All right, so this is very similar. Here, the horizontal component would just be the cosine of angle A, the vertical component would be the sine of angle A. But instead of writing cosine A comma sine A, I will write cosine A plus I sine A, which takes a little getting used to if you're not used to thinking this way. But just think about each of these as numbers. If this had been root 3 over 2 plus 1/2 I, that would tell you go horizontally by root 3 over 2 in the real direction, and then go up by 1/2 in the imaginary direction. Okay, so we've got those coordinates. B is just the same story. We've got angle B, so this should be cosine B plus I sine B. And now we're ready to actually multiply this out. I should have scooted this over a little bit. All right. So A times B. Let's multiply it out. A is cosine A plus I sine A. B is cosine B plus I sine B. Something tells me I'm going to need a lot of space here, so let's prepare ourselves. I'm going to do the multiplication right down here. All right, so cosine A times cosine B. Cosine A times I sine B. I'm going to put the I in front. So cosine A sine B. Now, I sine A times cosine B, so I'll put the I in front. Now, I sine A times I sine B is I squared sine A sine B. Okay, let's group together the real parts. And the real parts are each of these numbers that don't contain an I. So cosine A and B is going to end up just being a number. Like imagine A and B are angles. Cosine A is going to be a number between -1 and 1. This is a number between -1 and 1. So this is just a normal old real number. I squared, as we remember, is -1. And so this is also going to end up just being a regular old real number. So let's combine those two over here. So we'll have cosine A, cosine B, and then that's minus sine A, sine B. And so that's all the real part of our complex number. And then if you imagine taking this here and factoring out the i's, I'll have I times cosine A sine B plus sine A cosine B. Okay, you might be thinking, he said this was going to be easier. This is a lot of algebra. But the good news is we're done. We found the identity. So let's think about what we've ended up with here. These are the two components, otherwise known as like the coordinates of this point C here. We've already said that this green height is the same as the sine of A plus B because of SOHCAHTOA. But this green height is also the imaginary component of that number. And we've now just directly solved for the imaginary component of that number. So what we have is this right here should be equal to sine A plus B. And that's the identity we were looking for. This is the angle sum identity for sine. And you might notice that we have also, for free, gotten the other identity. If I think, what is that horizontal distance? By SOHCAHTOA, the horizontal distance, the cosine of A plus B is that adjacent side divided by the hypotenuse. So this adjacent side is just cosine A plus B, and that's the same thing as the horizontal component, or the real component of that number up there, and we've solved that here. So what took us like 2 days in class with quite a lot of work, and a lot of the work was very non-obvious, we've now solved both of them in less than 10 minutes just by multiplying two complex numbers together. So that's the power of the complex plane. It can make a lot of your work much easier to do. And it's almost easier to remember the process that got you here than it is to memorize the actual patterns of the identities themselves. You could pretty easily just derive this yourself every single time you need it. All right, I hope this was enlightening. Enjoy the rest of your day.